Good day, dear colleagues. My name is Hanna Ukhana, and I'm introducing our research on the topic application of filters with similar time in analog and digital signal processing both in robotic systems. Today, the technological equipment and production facilities components are equipped with multifunctional sensors and controllers. Under these conditions, wireless networks do facilitate the rapid collection of data, which after preliminary processing attend to the appropriate services of enterprises departments. Such circle embodiment allows employees to take in a timely manner their correct, informed, and well-grounded decisions. But the target task here is to achieve such a level of enterprises automation when at all production sites where possible both the equipment and automatic lines are operating without the personal's intervention. The role of personnel in this case shall be reduced to monitoring the machine's operation, thus intervening into only if some emergency situations occur. We face such problems when using various mobile platforms and specialized computer systems, as well as in systems for critical situations resolving. In this case, there is a problem of building the computer system components capable for their characteristic complex software and hardware rearrangement, depending on the noise signal environment to improve the efficiency of information processing in the input path. However, the signal initial processing begins in the analog path before the input signals conversions into input sequences. Signal processing in the system's digital part makes subject of a large number of researches. While not so deeply studied, remain the system analog part where there are several important tasks to consider. One of them is that the analog part also needs for an efficient rearrangement of analog filters characteristics. When designing the sensor signal processing path's analog part, it is necessary to solve the problem of cutoff frequency changes, as well as increase in the amplitude frequency response decline steepness. Building high-order filters is problematic. Therefore, in most cases, a cascade connection of low-order filters is used. For example, the second one. This task in robotic system arises when it's necessary to narrow the signal bandwidth in order to more accurately determine, for example, the location of an obstacle object. It's known that when a cascade connection, the transfer functions are multiplied. When multiplying the transfer function, the amplitude frequency response seemingly shrinks, while the cutoff frequency shifts to the low frequency region and the characteristic decline steepness increases. Thus, the purpose is to investigate the issue of changing the several low-order filters' cascade connection frequency response, and also estimate the basic low-order filter cutoff frequency at a given frequency of the final high-order filter for a given number of their connection. Four basic types of Butterworth filters, Chebyshev filters of the first kind, Chebyshev filter of the second kind, and elliptical filter were investigated. A cascade connection of 10 similar type filters was considered. The resulting amplitude frequency response was examined. For the Chebyshev filter of the first kind and elliptical filter, it has been found that the cutoff frequencies are shifted unevenly to the low frequency region, just similar to the effect revealed at Butterworth filter. In the bandwidth, the ripple level increases, that renders difficult the single pathing through the bandwidth. The elliptic filter in the bandstop also reveals the increase in suppression level. Thus, the cascade connection of first-order Chebyshev filters and elliptic ones does not allow to increase the filter's order without a significant amplitude frequency response, destroying in the bandwidth. Based on the results obtained, we can note that the cascading connection of the same time filter did once bring a flat amplitude frequency response in the bandwidth should be used. Such filters are Butterworth and Chebyshev filter of the second order. The study of cutoff frequency in the cascade connection of second-order Chebyshev of the second kind evidence that the amplitude frequency response here is the same as the Butterworth filters. The Butterworth bandpass filter was also investigated. It follows from picture that the cutoff frequencies are shifted to the central frequency, narrowing the bandwidth and increasing the amplitude frequency response decline steepness. The dependencies of the cutoff frequency shift and bandwidth narrowing are shown. It should be noted that all the obtained formulas have the same form. The implementation of such a formula is impossible in mobile and specialized systems which have limited computing resources. Therefore, we can represent the dependencies. We decompose the exponent function in the logarithm into a power series as follows. As in all problems, the approximation level is chosen assuming the relative error never more than 1%. The same error scale being assumed when choosing terms number and decomposition in a power series. In fact, calculation initial equation is a rather difficult task which requires a more advanced microprocessor. However, the relations obtained after decomposition are not easy to calculate due to a large number of simple calculations. When analog and digital processing parts building and connection basic filters of the same time, it's necessary to calculate preliminary the obtained equations on limited values and store them in memory for structure operational adjustment. This option of preliminary calculation is the most acceptable one. Thus, when cascading analog and digital filters with similar type, it's advisable to use second-order Butterworth and Chebyshev digital basic filters of the second kind, thus ensuring a good increase in the amplitude frequency response, decline steepness, and the cutoff frequency predicted value for the low-pass filter as well as for bandpass filters, Butterworth filters. Thank you for your attention.